I have thought about it.
Yeah, interesting.
Millisecond mazes. I thought of it. I was on the beach today and thought, oh, that's what you call them, millisecond mazes.
What kind of mood is your trombone in today, Keith?
Yeah, well, I gotta say, not great. If I'm brutally honest with you, anyway. But it's I've been doing some jazz with my kids, with my daughter. So we're doing online Zoom lessons with a local jazz group, and so we've been doing the A Train. So which is a bit of fun. It's quite tricky on trombone, though. But she's playing saxophone, and we get together on a Monday night. And a few other saxophones and another guy on a bass, and we all try and play along. Anyway, bit of fun.
Sounds fun.
Most fun you can have in your bedroom with a Zoom. Oh gosh, that sounds awful. Sorry.
I'm gonna have to edit the video.
That's not what I meant.
This is gonna be chopped out anyway. Okay, I think Sarah's going to take the lead, so I'll be quiet now.
Do you have a sense, Jason, as to how many people we expect to show up to the session? Like, should we start rolling?
Maybe give it like a minute or so.
Okay.
But yeah, don't wait too long. Just encourages tardiness.
This is the first of the discussion sessions so far, isn't it?
That's right. Yeah. Definitely have a quorum. We're over 30 people at this point.
Oh, okay. I can't see. Oh, hang on. Oh, look, I'm looking at the wrong spot.
All right. Hi, everybody. Welcome to the first discussion session of FRB 2021. Welcome from all over the world. Good morning, good afternoon, good evening, good midnight. So this first discussion session is going to be exploring the parameter space of fast radio transients. And we have a couple of slides we are going to, run through just to get the discussion started. Hi, Oliver. What I did want to just do first is lay out the expectations for this session and tell you what you're capable of doing to engage in this discussion. So first, we'd love if you raised your hand to speak. Put your hand up. There should be a little button you can find. If you're having trouble finding that button, shoot it into the chat, and of course, we'll help you find it. You are also able to request to share your screen if you'd like to show a slide or show some graphic that you'd like. We have to promote you to a presenter for you to do that, but just absolutely feel free to engage in that way. We would love to see some plots that somebody's whipping up in last minute. If there are any side conversations you want to have, of course, there's the Slack. Any small points you want to make, there's also the chat function in this Zoom call. And there's also still that Q&A open if you want to pose a specific question. We'll keep an eye out on that. So Pawan Kumar has raised hands. Are there any questions about the session generally? Do you have a question? Pawan? Nope, just put it down. I guess you were just testing it out. All right, feel free to test it out right now. All right, so let me just define, you guys can all see my slides, yeah?
Looks good, Sarah.
Great. So I wanted to make sure we define what we mean by parameter space of fast radio transients. There's lots of things that this could entail. And I just wanted to kick this off by just saying simply, I think there's a couple of different ways you can think about parameter space. One is kind of like the direct observational parameter space. Have we explored all the DM range that we possibly can? That's kind of limited by instrumentation. The same thing with rotation measure. There's a lot of limitations in our instrumentation that prevent us from going to the most extremes of these. Same thing with burst duration, fluence, scattering tail burst bandwidths. All of these can be confined by the way we actually set up our instruments. And many of us are pushing our instruments to go further in terms of, doing baseband recording and getting more sensitive, looking at more of the sky. There's also physical parameter space. So things like looking at dense environments and farthest FRBs and highest and lowest luminosity limits. These things are much more limited by a confluence of a lot of the observing parameter space. So it's something interesting to think about to me is all of the different instruments that exist right now. What is it that they're best at in terms of exploring not just the observing parameter space, but this physical parameter space? So looking at dense environments, we want to make sure we're not limited by some kind of burst width. We're looking at the highest RMs, also the highest DMs, and also getting good frequency coverage so we can look at the opacity. That's the correct way to look into these dense environments. Same thing with farthest FRBs. This is going to be most limited by looking at the highest DMs and also our sensitivity. And for highest and lowest luminosity limits, of course, this depends on our sensitivity, but also looking at a large region of the sky with very high sensitivity. And CHIME has done this spectacularly, ASCAP and others, DSA are doing this very well. So with that, I'm going to pass it over to Liam, who's going to present to you a few ideas. Go for it, Liam. I'll keep my slides up if you don't mind.
Sure, thank you. Yeah, that's a useful distinction, the two sort of categories of parameter spaces. I'll jump back and forth between the two, starting with the things that you actually read off of a dynamic spectrum. So I'll try to touch on the corners of parameter space that are currently unexplored or underexplored, starting with the ultra high DM, so say between 5 and 10,000 parsecs per cubic centimeter. I think with JP's work and Clancy's work, we know now that if you see a really high DM event, there's no guarantee that it came from far away. Whereas if you see a really far away event, it's almost certainly going to have a high DM. So in the former category, you can be locally dispersed, and you can imagine getting a really high dispersion measure from the local environment. Oh, there we go. In the local environment, maybe an H2 region or a still young supernova remnant. And people usually object at this and say, well, it would be free absorbed, and so you wouldn't see anything. But I feel like we don't really know the relationship between density, temperature, size scale to really be able to map that well into the DM opacity plane to decide whether or not you would actually see it. Another way you can get a huge DM is through a cluster intersection. So if you have a 10 to the 15 solar mass halo full of diffuse gas, you're inevitably going to get a pretty huge DM from that, and it could easily be a couple thousand units. And indeed, if you look at the CHIME catalog, the first CHIME catalog, the highest DM event, which is above 3,000, seems to come within about 1.2 megaparsecs of a cluster. So it's not clear that the FRB is actually behind it, but it's worth noting. Ultra fast events, I was really happy to see Kenzie's talk. Kenzie and co at the University of Amsterdam, and Astron really thinking carefully about microsecond FRBs. The ultra bright bursts, we have one example now, the galactic magnetar FRB from last year. It's worth keeping in mind that at a typical position in the universe, just extrapolating from source counts, you would never ever see a 100 kilojansky burst. It's just that we live in this very unique place where the number of magnetars per cubic megaparsec is quite huge, that we were able to see SGR 1935's megaburst. And so if we keep looking and we have large field of view 24/7, we'll see more of these. Next, if you go to the next slide, I think a totally underexplored, maybe even fully unexplored region of parameter space is at very low frequencies. So I dug up this plot, which is event rate, the all sky event rate on the y-axis as a function of observing frequency. This is a plot I used to show maybe 3 or 4 years ago to try to highlight that the constraints from non-detections at low frequencies were actually not all that strong. And that's because it's very computationally challenging, and it's challenging from a sensitivity perspective to do a blind FRB search below a couple 100 megahertz. So if I put on this figure now, the results from CHIME catalog 1, very tight constraints on the event rate at 600 megahertz, and also the constraints you get from the one detection of R3 at 150 megahertz, you see that the event rate is fairly flat in frequency. So even just from this one source, if you assume R3 is literally the only FRB in the universe that emits at 150 megahertz, that one source still gives you a reasonable number of FRBs such that the rate at 150 is comparable to the rate of the gigahertz. And so it wouldn't be crazy to revisit these low frequency blind searches and also search below 100 megahertz. some of the R3 bursts are still rising at 120 megahertz. So it wouldn't be that crazy if we saw something with LWA or low-FAR LBA. Okay, and then the last piece of parameter space that I think is largely unexplored. Do you mind going back one slide? Is time lag space. So we've started to explore this with some really great results in the past few months, searching for fast periodicity. So if you look at the microsecond periodic structure in Majid 21, this is from the M81 FRB, and then even more spectacularly in Daniele McKillie's talk from a couple of days ago in the Chime FRB at a couple hundred milliseconds. There's clearly interesting stuff going on in lag space. And if we start looking for gravitational lenses, then we open up this enormous range and time delay space from, in principle, 100 nanoseconds to 100 megaseconds, where you go from sort of Jupiter masses up to cluster masses that could give you lensing delays of 3 or 4 years. And so just very quickly, if you skip ahead 2 slides, sorry to make you jump around, Sarah, here, you see the spectrum of lens masses and time delays that you could potentially access with fast radio bursts through gravitational lensing. And you can do this with other explosive transients. You can do this with GRBs, and there are some claimed detections recently of gravitationally lensed GRBs. But in that case, you only have a very narrow window of lag space where you can only see maybe a couple of seconds or a minute gravitational time delays. And for supernovae and variable AGN, you're really limited by the width of the variation, which is weeks or months even. So I'll leave it at that.
So next, I am kicking this over, I believe, to Keith.
Hi. So I've got to thank Kendrick for these slides. He kind of put them together, and I think they were a really good summary of basically what the discussion's about. I'm seeing Kendrick's point here now. Yeah, I don't know, I'll just talk about them, I guess, and we can have a discussion. I mean, I think this is a really great picture you can see here of, you know, when we're looking for FRBs, we're often looking, well, basically, most of our algorithms are looking for broadband structure, and it was interesting to find out that Chime is also looking, you know, doing a search over a couple of different spectral indices. And by definition, then, if you're not looking for exactly what these structures are, you're going to be less optimally, you know, able to see them. So there's quite a lot of different, you know, parameters that we see, you know, like there's a huge range of morphology that we see, and we're not matched to them at all. So, you know, we're definitely missing out on some stuff because we're not using the correct statistic. Or the best statistic, or maybe a range of statistics. So I think that's kind of a, you know, and this is a really good plot when you see all this stuff. And I've actually put a couple of slides on of, if you go forward a bit, Sarah, you know, this one here of Pravir Kumar from the ultra wideband at Parkes. You can see this is a spectral occupancy of like 1%. It's 50 megahertz over 4 gigahertz or so, which is, you know, we're not looking for this sort of stuff. So if you could, you know, and we're often, we're not really looking over exactly this sort of fractional bandwidth either, but it's just interesting to note that there's no particular reason why we should expect, you know, things to be of the order of 50 megahertz. It could be kilohertz, you know, and maybe there's some really interesting science to find there, or, you know, maybe there's some good SETI things to search for on that kind of really tiny frequency scale. Is there something on the next slide here too? Maybe Kendrick, maybe you want to talk to this just because it's quite wordy and I didn't actually fully
Oh, sure, no problem.
problem.
This is just my pet thing anyway. So maybe
Yeah.
I should start by saying that I'm hoping to shamelessly use this discussion section to get ideas from the community for what we should be doing for the FRB search in Chord, which is the follow-up experiment to Chime that we're building now. You know, I'm interested in ideas for how to improve the search. one striking way in which current searches might be suboptimal is that they are limited to searching at millisecond-ish timescales or longer, just for computational reasons. And so we now know that FRB's pulses can be very narrow, and so we are potentially losing a lot of SNR. To take an extreme case, the CHIME search searches at 1 millisecond time resolution, but the narrowest FRB pulse node is around 60 nanoseconds. So we would be losing a factor of 130 in SNR for that burst. Unfortunately, there's some equations that didn't come through in the slides, so I'll just say them out loud. Unfortunately, decreasing time resolution is like the most computationally expensive thing you can do in an FRB search, since you have to decrease the frequency resolution in proportion, increasing the computational cost in proportion to sampling time to the -2. So going 10 times narrower in sampling time would increase the cost by a factor of 100. So one compromise I was thinking about is using a millisecond resolution search to find new FRBs. But then when the locations of those FRBs are reobserved and you know where to look and you know what DM to look at, then you could do a super high resolution search that might be able to dig out a lot more narrow pulses after coherently dedispersing to the previously found nominal FRB DM. So that's my pet idea. And I'm curious to share this pet idea with the community and see what other pet ideas people have come up with for improving FRB searches. Okay. I guess I'll go to the next slide. Thanks. I'm also really interested, so I'm like mainly a cosmologist by background, and so I'm also really interested in cosmological applications of FRBs. One thing in particular that I would love to, I think would really be an amazing opportunity is if high redshift FRBs exist. If in particular, if FRBs exist at redshifts greater than like 6-ish, then you could try to look for the plateau in the McCart relation, which would really powerfully constrain the reionization history. There was a nice paper recently on this by Beniamini, Kumar, Ma, and Quadier. I don't know, I wanted to highlight this since if you're a cosmologist, then constraining reionization history is actually like a huge priority. This isn't something that is supposed to be obvious, but just due to accidental parameter degeneracies, measurements of things like neutrino mass in the near future will be limited by degeneracies with reionization history. Like I and other people have written papers with a variety of ideas for trying to constrain reionization history better for precisely that reason. So it'd be pretty amazing if FRBs could do that. As a discussion question, I was just curious to hear from people what they thought about whether FRBs might exist at high redshift and what the observational obstacles might be to finding them. And then one more slide. And then finally, I was just, if you're thinking about cosmological applications of FRBs, then there's a lot of different things you might think about, like high redshift FRBs is something I'm interested in, but other examples include strongly lensed FRBs or like a list of possibilities. So I'm just curious to hear what everyone thinks about which types of FRBs might be most interesting for cosmology and how we would go about prioritize finding them in a search. Thanks, and thanks, Sarah, for letting me go over time.
No worries, there was no time limit. So yeah, so the way we want to structure this discussion is, there's obviously been a lot of interesting points made by these slides, and we'd like to keep the discussion open and flowing. Us moderators will be trading off, and we will move things along if we think it's getting too much to a sticking point. So I've noticed 2 hands raised. Pawan Kumar, did you want to say something? Let me unmute you. All right, go for it. I think I allow you to talk, but then you need to unmute yourself.
You should be able to hear me.
I can hear you.
Okay, good. So I can maybe address whether there are FRBs at high redshift. from a theoretical point of view, and also empirically, obviously not for FRBs, but GRBs. So first, theoretical arguments that FRB should be there at high redshift are that, well, if they are, if magnetars are producing FRBs, then we expect neutron stars to be there at high redshift. Whether there are neutron stars endowed with a strong magnetic field, well, we don't know, but we have very good empirical evidence that compact objects which are formed at redshift of 9 and 10 are endowed with very strong magnetic field. And that empirical evidence comes from gamma ray bursts. So many of you probably are, know about GRBs, but those of you who do not, gamma ray bursts require a compact object that is born, probably a black hole or a magnetar with very strong magnetic field is needed to launch this jet. So empirically, I would say that one can be very confident that these high redshift compact objects do manage to produce a strong magnetic field of strength of the magnetar field. So combining the two together, neutron stars at high redshift and the physics of producing a strong magnetic field is there at high redshift, I would say that it would be very surprising if FRBs are not there at high redshift. So
yeah, I think it's pretty convincing that there are going to be these magnetars at high redshift. The question is, where is the luminosity distribution's turnover? Is there a hard max? In which case there may just be a horizon unless you have an extremely sensitive instrument. Of course, you can lean on magnification bias from gravitational lensing. If you look at really high redshift quasars, then the probability that they've been magnified is pretty big. And so that might help with FRBs. But if there is a really hard Lmax, then we might be in trouble.
Well, so we addressed this question, we looked into this question in this paper that Kendrick mentioned, Binyamini et al. Paper. And what we find is that if we take known FRB, so we don't have to take very bright, luminous, high luminosity FRB, taking the garden variety FRB and placing them at high redshift at 8 and 9, a fraction of them, some fraction of them, something on the order of maybe a quarter of them, we would be able to detect even at high redshift. And by high redshift, I mean Z greater than 6.
With which instruments?
So we are talking here in the terms of instruments which have a fluence threshold of about a Jansky millisecond.
Nice.
So of course, it also depends on us being sensitive to very high dispersion measures. And I guess what's not clear to me yet is what is the limit of dispersion measure sensitivity for most instruments? And how does that work with the luminosity function and its evolution at high redshift? I think that's not so much been explored by anyone yet.
You know, in CHIME, we searched to max DM of order 10,000, but we've never.
You searched to that, but are you sensitive to that with your observing system? I guess it's assumed that you are.
We lose some signal to noise from channel smearing, but it's you know, it's not a dramatic. It's an order 1 effect, but it's not like a dramatic effect.
Okay.
Yeah, I was impressed by. Yeah. I was going to say I was impressed in the CHIME Catalog 1 paper. Well, first of all, by the effort to recover your selection functions, but how complete you seem to be in DM. I think that's great.
Yeah, aside from the channel smearing issue, I don't think that there are big obstacles to searching to high DM.
So Ron's hand has been up for a while. Ron, did you have a comment for this discussion?
Yeah, and I thought I'd get in early because I wanted to make some very general comments it started, maybe Sarah, your slide showing the different research spaces might be good to have on the screen at the same time. So my general comment is, first of all, as Keith, I think, pointed out, we have tension between finding new populations of FRBs with different properties and optimizing our search based on what we know about the ones which are found. Now, throughout science in general, and certainly discoveries in radio astronomy, we have always had that. And after the first few are found, so starting with Lorimer, people focus on optimal ways of finding ones that look like the first things you find. So this is a bias, sometimes well-defined, as people like Clancy have been working on. And sometimes the bias is unconscious, and sometimes the bias has a far bigger effect. Namely, we start designing telescopes to find the properties that we expect, because that's the most cost-effective thing to do when that's all you know. So, and I've been looking at the history of radio astronomy and the discoveries in radio astronomy, and you see this as a very common feature in new fields that open up. It is also the case that the application of something like Occam's razor, saying we need one kind of progenitor to explain all FRBs, has been a pretty hopeless model if you look at the history of discoveries. So I wouldn't put too much faith in that. But my final comments are, and the reason I asked you to pop that parameter space up is because if you look at why we know about FRBs at all, it is because of the instrumental changes which led to wide field of view. So just think about the fact that neither Parkes, which discovered Lorimer, nor ASCAP, nor CHIME were designed to find FRBs. The one thing they had in common was they have large FOV. And so I am surprised that you people are not seeing the field of view as the most important things. The biggest telescopes in the world, VLA, Arecibo, and now FAST, have found only a handful of FRBs. It may change a bit. And the reason, of course, is not that they weren't sensitive, it's because they don't have any field of view. So I'm a bit worried that this discussion is taking us sort of on a narrow path where we are so keen on optimizing that we are not thinking about how we can increase the parameter space where it's practical to do so, even if it is not in areas we expect. So that's my general comment. I had a specific comment on that last point about the highest redshift. I don't think we need fancy models to say there's going to be FRBs at the great distance. The universe would be very strange if it wasn't the case. But what I don't think has been helpful in the past is to talk about Emax, or the maximum energy, as a key parameter. It's just that you get less and less of them. The energy distribution will have some steep function. And so when you're trying to find the very rare, very bright ones that you can see at large distance, what do you need? You need a large field of view as well as sensitivity. So there's my very overview comments. Thanks, Sarah.
Yeah, as always, important points, Ron. Thanks for saying that. Keith, I think, has a response or a comment.
Oh, I'm just interested in the. I mean, I really like the cosmological probes of FRBs. I think that's the thing that excites me most. And I, in my mind, had the same plot as Kendrick had of just looking at the, some saturation point in DM, and as a probe of reionization history, I think, going after helium reionization, I think first would be just brilliant. But I guess one of the things from our perspective that's been quite tricky, and I'm not sure I'd love to have people's thoughts about this, is even with, with ASCAP, we get to, like sub 1 arcsecond resolution, spatial resolution, or precision rather. and you know, and with some systematics, and that kind of gets you out to a certain redshift, and we've been lucky to be able to get some you know, enough optical time to get spectra, for instance, and actually get a confirmed redshift. If you want to talk about things, you know, it'd be really exciting to get FRBs at such and such a redshift, but the difficulty would be is identifying the host at that redshift with really high, you know, again, you need really good spatial precision, but as well as that, and somehow you have to match these frames, but as well, how do you know that it's at redshift 6? I mean, it's a huge amount of time to kind of identify or to get a spectrum or even some kind of optical confirmation or infrared or whatever confirmation of a galaxy at that redshift. And there's no guarantee that that galaxy is visible at all at that redshift. So maybe you're only setting limits on it. So I think we just have to think a little bit about, you know, it'd be nice to get lots of FRBs, but at that redshift, but how do you really know that they're there? And, you know, how do we do cosmology that way? And I know, for instance, just to make one more point, I know, for instance, the continuum people working on ASCAP have been thinking about how to do certain cosmological experiments, which I couldn't explain to you because I don't know them, but they found a great deal of, they found you could get quite a lot of power by just putting different, you know, galaxies in redshift bins, just with very rough optical, you know, what they call it, not a spectroscopic redshift, color redshift, and just putting it in redshift bins is good enough to get you quite a lot of power. So I wonder whether, you know, when we're talking about this, we need to start thinking also about how to, you know, identify these sources at very high redshift and put them in some sort of redshift bin, and whether that's good enough to be able to do cosmology with. That's me.
Great, thanks, Keith. I did want to read the comment by Sterl Finney in the Q&A. I'm not sure everybody can see what questions have been put in there. He says, I think one challenge to identifying high redshift FRBs is that if one only has DM, once redshift is greater than 3, there might be a high host DM and lots of intervening halos. So only a small fraction of high DM events might actually be at high redshift, especially with higher fluxes. So that's an interesting point. Okay, I think I've done that. So we're trying to make this fair. So we're handing off moderation duties in turn, and I'm going to hand it over to Kendrick to lead the discussion now. You there, Kendrick? You got
yeah,
unmute.
sorry. So yeah, I suppose I guess if it's up to me to ask questions, I'd like to start by just throwing out the question of which parts of the parameter space you know, people are of the FRB parameter space people are most potentially excited about. Like for me, I think it's high redshift FRBs if they exist, but I'm curious to you know, ask that question to the community.
What about rare FRBs as the key to where we go next?
Rare along which axis?
On any axis. That is, we already have a few which are quite exceptional, and to some extent are misleading because you follow the wrong line. But think about millisecond pulsars. They didn't come about because somebody said there's going to be millisecond pulsars. In fact, the designs of pulsar searches were done to not have to search for milliseconds. Then all of a sudden one was found through its polarization properties. My other comment is, yeah, look at a diverse range of ways of finding these things.
Yeah, I mean, one extension on that point might be as well deviations from a 1/frequency squared law, and which would, lead to the discovery of things in different environments than we would have expected. Non-cold plasma, right?
Yeah, I've thought about our match filters are detect a very narrow range around frequency to the -2. Unfortunately, broadening that range is really computationally expensive.
Did any of your injection tests include bursts with strange morphology? I mean, I guess you have Gaussians that end up.
Yeah, at the moment, no. We just simulate on like simple bursts with power law spectra. So I see that Emily has her hand up. Sorry, everyone. I'm learning about the how to be a Zoom moderator right now.
If you have any questions, let me know. So you should be able to click allowed to talk, and that would get her to be able to talk. But if you call on people, I'll be happy to push them.
Okay, I think I figured it out. Yeah?
Yeah.
Okay, cool. Yeah, so I mean, like we're talking about high DM FRBs, but I think the low DM ones are I think they hold a lot of promise on the exact opposite end. Like within Chime FRB, kind of seems like the few FRBs that are like low enough DM that you can pinpoint them to a local group galaxy are turning out to be not only incredibly interesting in their own right, but also incredibly interesting as these kind of bridging sources that tell us more about the population as a whole. Would we actually, if we had a FRB at a redshift of 0.5, would we be able to say it was in a globular cluster? But the power of the M81 source is that, you actually can say very precisely where it is in its host galaxy and, localize it to a specific region and actually maybe say something about multi-wavelength emission. So I think there's a challenge to finding low DM FRBs as well, maybe less of a instrumental challenge, but maybe more of a classification challenge, convincing ourselves that these things are actually extragalactic sources, that they are not in our halo, or that we understand the Milky Way halo. So I guess, there's on both ends of the extremes. I guess one thing I'm kind of curious about from other people here is, how important is it for us as we study the larger FRB population to understand our own Milky Way and understand our halo and actually convince ourselves that really low DM FRBs are in fact FRBs from other galaxies.
Can I just ask a quick technical question to the Chime people? Looking at your DM selection function from the Chime FRB catalog 1 paper, it looks like your completeness is lower at 100 units than at 4,000. So why is that? Why is it harder to see an FRB with DM 100 than 4,000?
Yeah, so the reason is buried in the guts of how we do the RFI removal. So our RFI removal processing, this is a super technical Chime specific thing that other experiments may or may not do. But we found it necessary to include a filtering step, which independently for each time sample, high pass filters in the frequency direction. I never really had a good understanding of what we were filtering out, but empirically, if we remove that step, we see false positives all over the place. And then if you think about what that high pass filter does to an FRB, like an FRB at DM0 would be perfectly removed. You would remove 100% of the signal to noise. And in general, the fraction of signal to noise which is removed is an increasing function of DM over pulse width. So we end up with a big SNR penalty for low DM FRBs, especially if they are wide. It's probably worth revisiting that now that we know that low DM FRBs are actually might be specifically interesting to optimize for.
And then on the other end, what's preventing us from detecting high DM events? Because it looks like it's not about interchannel dispersion or incompleteness in your pipeline. Seems like it's probably about sensitivity.
Yeah, I think that they're just faint. I see Adam Dollar has his hand up next.
Yeah, so what I've been trying to formulate in my mind, the best way to say, I'm not sure if I'm going to say it correctly, is I think the nearby events are very powerful in terms of being able to do multi-wavelength follow-up, do detailed local environment follow-up, et cetera. But to date, the the nearby events that have been found have not been truly representative of the kinds of FRBs that we see at higher redshift so far. So, like the SR 1935, that's not quite there in luminosity space. The same thing for the globular cluster one. So I think something that would be super powerful would be finding an event that is relatively nearby, but is more representative of the higher redshift FRBs that we find. And so obviously that's going to be, would be extremely bright, but will be quite rare. So I think that argues for the field of view approach that Ron was talking about. And the other thing that I was going to say, which has like almost nothing to do with that point, is that I think that the other the highest impact cheap thing that we can do in terms of getting more out of the FRBs we detect is to commission baseband, real-time detection, classification, and baseband recording at more facilities, because that's what we can really use to go back and squeeze more out of the FRBs that we do find. So I don't know if anyone else wants to add to or rebut any of those points.
I agree with your first point. I'm not really sure what to make, especially of the M81 FRB. It sort of looked like there was a march down, but I don't really think there is. There's clearly like some temporal structure, there's some weird frequency structure, but it doesn't look like other repeating FRBs. And as you say, it's not quite there in luminosity space either.
I want something super bright and broadband nearby, and narrow, preferably.
Totally agree about baseband data.
I mean, the baseband data thing that unlocks the possibility of looking at, or trying to definitively prove multipath propagations like gravitational lensing or something like that. It's a lot more of a stretch, obviously, and there's a lot of things that could still destroy it. But if you get it, then you've got everything. You've unlocked a whole new, order of magnitude of things you can do.
Sorry, could I interrupt? I just want to, has anyone actually looked in baseband data for any evidence of, I mean, I know we have, but anyone looked for any evidence of gravitational lensing in baseband data yet? Like echoes?
There's a really nice poster that Brian Gainser pointed me to, poster number 15 by a grad student called Zarif Qatar. And he's doing this analysis on chime data, it looks like. So they're really digging into it and figuring out how to remove PFBs and all the nitty-gritty stuff.
Brian Gainser has his hand up next.
Yeah, hi. I was typing in the chat earlier and I dropped out, so I'm not sure if it came through. But so we do have some candidate very high DM bursts with chime. So we have a citizen science program with chime on the Zooniverse platform, and citizens have found some we give them all our low signal to noise candidates, and they have found several candidates with DMs of 4,000 to 8,000. And some of us have looked at those ourselves and said, yeah, that looks real. So individual bursts, we don't have intensity or baseband information for these. So for an individual burst, there's not much you can really say except, yeah, that looks real. But as we accumulate a sample of them, we can start to look at their fluence distribution and their burst width distribution. and start to see if this is consistent with a high redshift population or a high DM host population or artifacts. But just by eye, they just look like every other FRB.
Or a coincident cluster. It's worth checking.
Yeah. So we've got about a dozen of them so far, but the number will just keep going up.
Next, Ron Akers has his hand up.
Yeah, sorry for the delay, but you've got to find where the unmute button suddenly appears. Two comments. Keith asked a specific question. Has anybody done baseband searches looking for lensing? I suppose he meant by looking for the coherence between the different paths. We did do that search with some ASCAP data, but JP and I got quite disillusioned because it is destroyed by scattering and maybe not a very effective procedure looking for the actual coherence. And of course, it's hugely computationally demanding as well. But the scattering will destroy that coherence on two separate paths very, very readily. Since I've got the microphone, I thought I would make another general comment. It followed by, following Adam, if we want to find interesting nearby ones, namely ones which are in the same energy range as the more distant ones, that is finding they're going to be rare. They'll be there, there's just not going to be so many. So I wanted to draw to your attention, because I haven't even seen it discussed in this meeting. A few people have been looking at really large field of view, that is all sky monitors for FRBs. And in particular, the prior proposal by Denny Price to use an SKA low station, but reconfigured as an all sky search engine. His motivation was to look for SETI, but the surprising result was it should find plenty of FRBs, and it will find these extremely rare ones. They're going to have to be very bright because the sensitivity isn't huge, but it's up a factor of 1,000 in field of view, and that is a big factor.
I'm going to talk a little bit about that on Wednesday, where Vikram Ravi and I have been discussing a sort of million FRB survey and what that would take. And the answer is basically a dense phased array, but with a lot of collecting area. So you need about 15K dipoles to match Chime's collecting area. I think at 450.
Yeah, but why do you want? No. But you want the rare, interesting ones, which are bright enough that you'll find them. Never mind the faint ones. You're trying to do too many things at the same time.
No, but your experiment is a subset of mine.
Yeah.
So
okay,
I get all the bright ones as well.
Sure, but getting large field of view and a large collecting area is a massive compute problem, because you've got to analyze every possible path through the system.
Well, we're starting with GREX, which is a single dipole, and then building up.
Yep. Okay. The other experiment we're looking at is there's a phased array feed, very low T-sys phased array feed being built for parks. We've done the calculations. Ray Liu put the numbers in his model. You just sit that on the ground and point it up. It'll find an FRB about one a week, which is pretty good actually. And these are extremely bright and will include a local sample.
Wei-Li seems to think you can preserve coherence even in the case of scattering.
Yeah, there's a comment from Wei-Li in the chat.
I think he's got his hand up as well.
Oh, sorry.
Yeah, I mean, it's not a matter of me thinking, it's measured, right? It's measured that because we see scintillating scattering tails. So we know the multipath propagation does not decohere. And this also already proves that the scattering is not in the IGM or intervening halos, as had been proposed by some people. So this is observationally evident that at least for some or many of the FRBs, the multipath does not get erased by scattering, which it would if it was due to intergalactic scintillation. So I think one should keep searching. And I thought there is a talk in this conference by Calvin, maybe, who is actually doing this search on CHIME data. So there is and the conclusion is that depending on the scattering regime, of course, if you're scattered enough, and depending on where the scattering is, there is a regime where it could happen. But on the other hand, the generic parameter space is not destroyed.
Yeah, Wei Li, I'm sorry, I wasn't referring to scattering, local scattering, which will not destroy the coherence. Agree.
I mean, any scattering. So this is true for that's measured, right? That the scattering tail of FRBs is the one that we see that are still scintillating. So in fact,
yeah, but that scintillation can be imposed after the scattering tail formed.
Exactly. So that's why lensing, if it's induced after scattering forms, will still form an interference pattern, just like scintillation does. It's the same effect. I mean, whether the lens is a plasma or a gravitational object doesn't change the existence of an interference pattern at microseconds time delay.
Well, it depends how many scattering paths you've got.
Well, I'm just talking about an empirical measurement. I'm not talking about an expectation. That's a different story.
Okay, I'll think about it.
And again, I encourage in our paper on Masuri et al., we do go through that argument as to why this measurement makes that implication. And we'll hear more from Kelvin at this conference.
I think Calvin's saying that it's Zarif, but
thank you, Zarif.
So Liam, I'm sort of curious why your million FRB search is dipoles and not little dishes. Like naively, if you fix the number of feeds, then the FRB detection rate goes as the dish area to the 1/2, right? Since the field of view goes down as 1/A, but the forward gain goes up by a factor of A. And if FRBs have a Euclidean distribution, then that's a factor of A to the 3/2. So if you were just optimizing for, there's the question of whether it's more interesting to optimize for fainter FRBs on the whole sky, or to go deep and look, brighter FRBs in the whole sky, or to go deep and look for bright FRBs, faint FRBs. But if you were just optimizing for total rate, then I think the optimum is to put a small dish on each feed whose size is determined by the criterion that the cost of the dish is comparable to the cost of the feed and the electronics.
Well, I guess with dishes, yeah. I actually don't know if FRB detection per unit cost ends up being cheaper in that case, but
I guess unless you're
with a dense phase array, you're going to build up a stair radian of field of view. And if you have a 4-meter dish or 5-meter dish, you're not going to.
Yeah, I think you win. I think you still win though, because the FRB luminosity function goes as like flux to the -3/2, not flux to the -1.
Yeah,
it's a minor point, but I was just curious. The exception maybe is at like really low frequency if the lambda squared effective collecting area of a dipole is like already pretty large.
Well, that's the thing. I mean, you can't do this at L-band. You have to do it at lowish frequencies where lambda squared is reasonably big.
Yeah, okay.
And it doesn't take that many dipoles to get up to 10,000 square meters.
Did you say you were someone else was giving a talk on it?
I'm giving a talk on Wednesday where I'll touch on these things.
Cool. Yeah, it sounds interesting.
But you're fighting lambda squared, cubed, isn't it, for the DM search impact as you go down in frequency. So you pay a penalty in the compute, and the computers may be more expensive than the telescopes, Kendrick.
I think channelization is the most expensive in that case.
Yeah, I'd be more worried about the cost of beamforming than the cost of the FRB search. Even at low frequency. So maybe the answer is no, but since I have the floor for another 6 minutes, I'll ask if anyone has any thoughts on how to make FRB search algorithms more optimal. This is something that I'm really curious about because we're thinking about the design of the chord search now. Oh, Adam Deller has his hand up.
So do you mean optimal in the absolute sense or optimal in the in terms of computational intensity?
Oh, I'm more worried about optimizing event rate at like reasonable computational cost.
So oh, sorry, go.
Sorry, go on.
So I was thinking, so one very simple example is that we know we would find more FRBs if we channelized more finely and integrated less and looked for shorter FRBs, because there's definitely shorter FRBs to be found that we're reducing our sensitivity to at the moment by the channelization parameters that we choose. But do we care? If we have a certain quantum of dollars to spend, or euros, or whatever currency you like, is it worth spending that to make sure we recover a higher fraction of temporally narrow FRBs, or would we rather get a larger number of all FRBs and hence a larger number of short FRBs as well, but just still knowing that we're only ever scraping the top of the luminosity distribution for those short ones?
Yeah, it's always been a thought in the back of my mind that I would love to increase the resolution of the FRB search, but it seems to be that seems to be a very expensive direction in parameter space, right?
Absolutely,
and I don't see any way to get around it. It seems to just, the computational cost just seems to go as the square of the resolution.
Yeah, and if you have a baseband recording system and a real-time triggering system, then as long as you trigger quick enough, then of course you can always go back and look at the higher time resolution. And so for the brighter ones, you'll get the high time resolution properties of the subset that are bright enough for you to find. And so the thing I'm trying to frame is, is that good enough? And are we happy to accept that we lose, an increasingly large fraction of the very short ones? And my guess is yes, and we're better off spending our compute dollars somewhere else, like for instance to do semi-coherent dedispersion to increase our sensitivity at high DMs. But I'd be curious to hear what other people think.
Well, Kendrick, in the case of chord, can't you search, say, the top quarter of the band where the interchannel dispersion smearing is new squared better, and do an ultra high time resolution search up there?
Still goes as it's still equally.
You need fewer channels is my point. You could do a hybrid channelization.
Yeah, you could search a fraction of the band at higher resolution. That's true.
And it's not as if the FRBs are going to extend from 300 megahertz to 1500 megahertz. So you have to do subband searching anyway, probably.
Yeah, I do really like the idea of sort of coherently dedispersing at a coarse grid of trial DMs, and then incoherently searching around those DMs. It could be a very nice way to improve sensitivity to the high DM FRBs.
I mean, the other thing you can also, you can have a flexible experiment, right? So some of the time you do a coarse search, and some of the time you sacrifice field of view for time resolution or something like that, or whatever it is. Given that you've got a fixed size of computer, you can you know, you can go after different things, different science cases at different times. That's, you know, that's an approach that we're kind of trying to, well, that I'm thinking about on our side, which is, you know, is there, you know, times when you want to do, say, high DM searches at low time resolution, you know, given that you can't fit everything in the box at the same time, try and have a flexible system so that you can spend some of your time, you know, and a bit more like a traditional telescope, right? You know, there's lots of people who want to do particular types of science, and so you configure your machine to do that type of science for a while, you know, in proportion to the scientific impact.
To get a sense for the intrinsic pulse width distribution, because we really don't know that. And it
Yeah.
may be that there are as many or more FRBs between 50 and 500 microseconds as between 500 and 5 milliseconds. And so,
right. And someone like, you know, a machine like Chime, I think I mean, I don't know how easily it is to reconfigure it, but you've got the kind of fundamental metal parameter space, right? So, you know, if you could, you know, make the field of view a quarter of the size and then spend 6 months looking at, you know, 4 times the time, well, I guess half the time resolution, or I don't know, something like that, then maybe that's interesting. I don't know. I mean, there's maybe a trade that you can do in terms of configuring your machine. I mean, it's a harder machine to build if you're asking it to be flexible. I mean, from personal experience, it's a harder thing to build. But you know, I find that a helpful way of thinking about things.
Some really fun suggestions in the chat. Wheeling suggests offline compute resources like FRB at home. Super fun idea. I guess it's too much bandwidth though for a blind search anyway. If you were restricting to, like, if you knew where to look, or if you wanted to search one beam really well, that could work.
Well, I mean, I'm saying with VFaster, which was searching all the VLBI commensal data anyways, there one might worry that Socorro is not well equipped to power a big computer cluster. However, if you just say anybody who wants to download any chunk of it and just search it at home, you might get crowdsourcing. Everybody searches, you know, 5 minutes worth of data, and you've got 1 billion people searching, and you might be able to get some mileage on that particular very unique, very specific, very low TSYS, high sensitivity data set, very niche application of.
So Emily has her hand up.
Yeah, just thinking along the lines of what Keith was talking about, if you have like a tunable system where you can say like, okay, today we're going to look for, you know, we're going to look in this area of the parameter space, and maybe we'll do that for like a couple months, and then we'll retune and look in this area of the parameter space. I think an important thing to kind of made me think about from the perspective of watching the Chime team work so hard on this is that one thing to think about that we haven't really talked about yet in the context of exploring the parameter space is exploring our completeness in the parameter space. So you can find all of the interesting FRBs that you want in various areas of the parameter space, but if you don't understand your selection function and you don't understand how complete your telescope is in that time that you're searching over a certain type of parameter, then you know, maybe it's not actually population-wise all that useful. So yeah, I'd be interested to hear other people's thoughts on, I like the idea of like, just if you have a flexible instrument to look in different ways, but how to make sure that we understand our completeness or lack thereof, and how we understand our selection functions.
Yeah, so well, in Chime, as you know, of course we do injections, but the challenge is always making the injections as rich as the landscape of FRBs, like the mimicking the complex morphologies that we see in FRBs. But I'm wondering what other experiments do. I don't know. Does anyone else have any thoughts on any suggestions for measuring completeness? Adam has his hand up.
Yeah, I think that injections are really the only way to go, but you identified the crux of the problem, which is that you can only test how good you are at recovering things you know about. And I think going even one step further than that, even just reproducing the full range of the richness of all the things that we already know about, modulated by all of the instrumental effects that we do know about, you have to do a lot of injections to sample that parameter space fully, and that's only the things that we know about. It doesn't get you the unknown unknowns. So and it is limited by how faithfully you can reproduce all of the true instrumental effects, because of course, we don't tend to inject FRBs at the voltage stage or into the front end, directly. We do it in the power normally. So, I think we can and should put more effort into doing it as faithfully as possible, but it's never going to be perfect. And I think making the code public that we use to do that, and describing what we've done really carefully in the papers, is very important too. And I think that's come a long way already in the last year or two, compared to the early days of trying to characterize completeness of FRB surveys.
I totally agree. Maybe I'll switch over to Ron next, who has his hand up.
I was just going to expand on that argument about the need for completeness, triggered by Keith telling us, hey, I'm going to have a variable search space. So I was thinking maybe we should design the test injection right into the systems from the beginning, not as some add-on at the end. And as Adam said, if you put it in somewhere downstream in the process, you're making assumptions. So why not inject artificial FRBs continually in any system we design in future? Because that would be so valuable. I think the gravity wave people do that much better than we do.
Ron, everyone else is doing it but us, because I'm lazy. I think it's the short answer. There's a lot of pretty good injection people. Sounds bad. Yes, it's happening a lot more on other machines than it is in ASCAP at the moment.
But is anybody going back to actually injecting well, you can't generate a far field injection system very easily, but you could put electromagnetic pulses into the antenna and cover a very large amount of the system.
Yeah, no, I don't know if we've worked at it at that level, although, maybe we could put something on the moon. The moon's not really far enough.
Willie proposes using the Parkes microwave oven for injections.
Speaking of that, we are working on a program that's researching all of the old archival and some of the new FRB data, and doing a full completeness assessment of all of these. So this is something that Shrita Jagarwal is calling the petabyte project, because it's well over a petabyte now that we're dealing with. But we are going to try to do some kind of full assessment of completeness in old FRB surveys. So that should be coming out in the next 1 to 2 years, and hopefully we'll be presenting on that, some initial results from that in the next year.
Cool. So Emily has her hand up next.
Oops, no, I don't. Sorry. I guess I forgot to lower it.
I do that all the time. Okay. So this might be a natural point for me to hand things over to one of the other panelists. And maybe Keith can go next.
Sure. Well, I can't see any more questions on something. I did have a question for Kendrick, though, seeing as we're here. You'd mentioned your idea of following up or looking for repeaters. how is that different from what kind of happens probably already with people taking, except that it's the same telescope? So currently, I think, Kai might find a repeater, someone else goes to a big single dish, they set up their coherent dedispersion system and then look for pulses in a, baseband, or, coherently dedispersed thing. Is that, maybe I did not understand what you're proposing there.
Oh yeah, so I was just making the point that like a microsecond resolution FRB search is too expensive for a blind search.
Yeah. Okay.
But you could zero in if you wanted to like zero in at a particular sky location in DM, then you could do it. So a natural candidate would be like the sky locations in DMs of previously known repeaters. And like how much that might help would depend on whether repeaters are emitting a bunch of faint narrow pulses or not. Like if they are, then you might like really find a lot more pulses, and it might help you test whether a blindly detected FRB is a repeater or not.
Right. Yep. Okay. Cool. Vishal has a question in the Q&A for Liam. In your FRB rate versus frequency plot, have you considered any intrinsic beaming effect? For example, do you expect the same FRB rate at 6 gigahertz? You want to take that one, Liam?
Yeah, sure. This is just a plot that I gathered through non-detections and various other papers. This is purely empirical. Let me just share it again quickly. But yeah, that's interesting. You could definitely have a narrow beaming angle at higher frequencies, which could change the rate. I haven't included anything above 1500 megahertz, even though I could have. Yeah, I guess 121102 has been detected up to 8 gigahertz. And maybe that's true for R3 is 4 gigahertz or something. I can't really remember what's happened above 2.
To my knowledge, magnetars have been detected up to 100 gigahertz. Is that right? Someone would know.
Yeah, the galactic center magnetar, I think, at above 200 gigahertz.
Oh yeah, another thing I meant to say about high redshift FRBs is that, of course, the frequency gets redshifted. So an FRB that's whose intensity spectrum peaks at 1000 megahertz in its rest frame, say. If you put that FRB at redshift 9, then it's now showing up at 100 megahertz. So I think I'm really excited about the low frequency searches, like LOFAR searching for finding high redshift FRBs.
Yeah, I agree. And the things that you're scared about with these low frequency searches don't really matter anymore, like scattering, because they happen in the rest frame for the most part.
But yeah, I guess scattering redshifts away is like 1 plus c to 1 plus c cubed, something like that.
Yeah. Could you, if you saw this might be a dumb question, but if you saw a FRB from reionization, wouldn't there be like a 21 centimeter Gunn-Peterson trough effectively? Where it gets absorbed up until the 1 plus z times 1400 megahertz?
That's a really interesting point.
I don't know how you disentangle that from the patchy intrinsic spectra that we see.
We've been thinking, well, I know we've been thinking about H1 absorption against FRBs, but maybe not Gunn-Peterson style things.
Yeah, I remember Wei Li used to talk about that as a way of getting a host galaxy redshift, if there was significant absorption in the host, but there just weren't the column densities that you needed.
Yeah, the signal to noise is hard.
Yeah, would that be detectable? The 21 centimeter line is pretty faint, right?
Yeah, I mean, for a normal FRB in a host galaxy, no, I think is the answer. But if it were before the universe were ionized, then probably.
Yes. point made. It depends on the spin temperature of the medium. Yeah. There was a question up before. Ron, I think, asked a question about can you use quantum computers to search for FRBs? I didn't bother to search the Google for quantum search of FRB, but data. But there's an algorithm called Grover's algorithm that uses a quantum search for a phone book. But I don't know if it's used for well, there's lots of treatments of noise, but I don't think it's designed for noisy data as such. But it did point me towards another thing, which was one of the very most elegant papers I ever saw on the subject of searching, which was using an algorithm called the Viterbi algorithm to look for, which is used in telecommunications, but funnily enough, but it was to look for noisy, like random walk signals in gravitational wave data. I thought that was very elegant. I don't know if it's really directly applicable to, well, actually, I think it is applicable to FRB searches in the across the frequency domain. If you want to kind of maximize the signal to noise, if you want to look for something that's patchy along frequency, and you kind of have some model for how often it sort of pops up in above and below your signal to noise threshold, you could use an algorithm like that, and it's provably optimal in certain circumstances, but I'm not sure whether computationally it might be a bit expensive. I don't know if Kendrick, you've thought about these things. I've just kind of looked back at that paper and went, oh wow, that looks clever. I should think about that.
Yeah, for sure. I think we want to do something like that in court, some sort of search over scintillated or wandering spectra, and the algorithms that would be computationally feasible would model that spectrum as some sort of like random walk-like process, like the Kalman filter or the Viterbi algorithm. I'm just not so sure what the right model is, right? If you have if you have a model you believe that models the the likelihood of a given spectrum as being the likelihood of a random walk, then you can code up the optimal statistic for that, like dynamic programming based statistic for that model.
Right.
But what's the right model? I think that's the more difficult question.
Yeah. Well, I guess you could approach that from just purely empirically, just looking at the past FRB spectra that you've already got. I mean, you've got enough samples, but I guess that what you're trying to avoid is finding more of the same, right?
Yeah, that's true.
Right.
Yeah.
Damn. Yeah. Anyway,
the only reason in Chime we just search for power law spectra is that when we started writing the search, there were only like 20 known FRBs, and it seemed like a reasonable conjecture that they were all had power law spectra, but now we know that's like a terrible model.
Right. Matthew Bales points out that Viterbi optimizes for drifts from a linear drift. Okay. Maybe you could pop on and raise your hand, Matthew, if you want to explain that a bit more. But Ron's got his hand up. Ron? Far away, Ron.
I was going to comment on that little H1 discussion. Liz Marnie does a little bit of FRBs, but is mostly doing H1 absorption. So we went through all the ASCAP FRBs to see if there were any which in their spectrum had a peak where the H1 absorption would be, and if there were any, whether there'd be enough signal to noise. The answer was no, there were no good cases. And I was really wondering if anybody else has done this. You don't have much integration time, of course, to do the H1, but some of the bursts would have been strong enough to see an H1 absorption. So in principle, it's possible even with existing data. But there were no candidates in our sample that were any good.
I mean, there might not be enough examples outside of ours, Ron, that have redshifts that you. I mean, you were looking for associated. Given the redshift of the host galaxy, you're looking for H1
true. In
associated
fact,
with the galaxy.
yeah, you've got to have a redshift, of course, otherwise you can't do it. It's not accurate enough to know where to look. Yeah, so we were looking at the ones with redshifts. Agreed.
Anyway, I'm sure there's more redshifts coming up for FRBs. I'm almost certain. So anyway, those people can chime in. Excuse the pun.
Calvin, do you mean because the FRBs would have to come from so far away? 0.8 to 2.5? Calvin says they tried this with chime data, but it's hard between 400 and 800 megahertz.
Right.
Makes sense.
Presumably doing a search for H1, not having specific redshifts. So we were looking at the case where we, just in fact, to see what we could find out about the environment of an FRB, not to find the redshift of the host. So if you knew where the redshift was, you can do a slightly more sensitive detection.
Yeah, I just meant that if you're looking for local absorption and then for chime, the FRB would have to come from at least redshift 0.8.
Yep.
And it looks like most of them are kind of 0.3 to 0.5 from the cross correlation work.
So some comments in the chat. Yes, a few people are just pointing out that it's difficult if you've got ratty spectra or if you've got patchy spectra and you don't know the redshift. So I think the key there really is to have a redshift, but it's difficult to do blind. Matt, if I can invite Matthew's got his hand up. Matthew. Look,
hello.
Innocent there. I'm not. I promise I'm not spray painting a wall. Is that what that face is? Are those guys painting a wall?
Who?
Sorry, Matthew. We can't see you, but I can see a picture of you standing in front of a wall with some guys painting it. Anyway, fire away with your question, Matthew.
It's actually a supercomputer being painted with two black holes. But
oh, there you go. Right. My mistake.
Yeah, I'm not sure why my camera's not on, but anyway. Yeah, a lot of the FRBs, if you think back to Vikram Ravi's science paper, they were very bright, kind of like scintils. And so it would be easy for one of them to correspond to the redshift of something you're looking for. So convincing yourself that you haven't got you've got a real absorption feature, given the narrowness of any H1 absorption is very difficult. That was all.
Thanks.
I'll try and work out how to make my camera live.
Matthew, yes, it seems to be dead. Calvin Lung has his hand up. Calvin, let me click the button there. There you go.
Hi, I just raised my hand a couple of minutes ago just to say that we have tried searching for H1 absorption in unlocalized time FRBs, and it's hard because we don't know the redshifts. And everything just hurts you because you have lower and lower signal to noise and things get far away. And the main search background we ran into is actually FRB scintillation. Very fine spectral structure. So it gets kind of hard to disentangle that. So I agree that like the next best thing you could do is to localize these things and do a targeted search. Yeah, that's all.
Thanks, Calvin. Matthew still got his hand up in the thing. Matthew, I don't know if you meant to have that up.
No, I'm just trying to find my camera turn on button.
Okay. Cool. How are we going for time here? We said we go till 12, right?
Yeah, I think so.
Okay. Bless you.
I've got a question for the group.
Far away, Liam.
I feel like we haven't talked that much about periodicity at this meeting yet. So as of like last week, basically, we now have periodicity or quasi-periodicity from a few microseconds in the M81 FRB to a couple hundred milliseconds to 16 days and maybe 160 days for R1. So there's a lot of interesting stuff going on in lag space, which, as I was saying during my slides, is sort of underexplored. So what are the current efforts to look for periodicity? I guess I'm more thinking of R3 and R1 now. But if you remember Dongzhi Li's talk last year when she was talking about discovering the 16-day periodicity in R3, she pointed out that it was kind of one of two sources that they had enough burst for to even do this search, which means if it's not generic, it's at least sort of common. It's hard without Chime, to be fair, but yeah. Any updates on that front?
Well, of course, there's now like the Daniele Michele's paper on millisecond scale subburst periodicity, which is a different kind of periodicity.
Yeah.
Which I think is a really exciting result. Aside from that, we don't have anything new to report. Internally, we're doing lots of periodicity searching and hope to find something new soon.
Yeah, that one's really interesting. I was convinced by the Majid et al. 21 sort of 10 microsecond periodicity that this was just pulsar microstructure, basically. And in pulsar microstructure, there's this relationship between the period of the microstructure and the spin period of the neutron star, which is roughly like 1,000 times the microstructure period. So that would make this a millisecond pulsar, but Daniele's one is 100 milliseconds or something in period. So clearly something else going on. Oh, you're muted, Keith.
Yep. Dongzhi Li says, for the long-term periodicity, the number of sources I could search is not improved a lot within a year. So, yeah, there's a source count restriction there. That's my kid playing in the background. I had a question actually about, we're a bit. I actually haven't checked the Chimes selection function, but I guess it drops off as you go to wider bursts. Do we think that there's some value there that we're perhaps missing? I mean, does the kind of width of the population kind of die off before we think our selection function starts to bite us, or is there meat out there that we're missing out on? Sorry for the vegetarians, you know what I mean?
Yeah, no. In Chime, we're running into the the actual timescale of the 1/f noise. We have to detrend on timescales of a few hundred milliseconds. That's the that's the main obstacle for us searching for wider pulses.
But do you think that there's do you think that that's hurting? Well, do you think that there's the population? Do you think there's something out there? I mean, I haven't really looked at the statistics well enough to know whether the population's dropping off well before you get there anyway.
We do see the distribution start to decrease at high intrinsic width, even after correcting for our selection.
Mm-hmm.
But that's a statistical statement. I think it would still be really interesting if there were it's still interesting to ask the question of whether there are a few FRBs with, say, 1 second widths. And I think that's a question that we just can't answer in Chime with our 1/f noise.
Yeah, I mean, we could do that using alternate techniques too. I mean, we've on ASCAP at about the 1 or 5 second level, we're doing that with ASCAP in an image sort of search. In fact, one of the FRBs we detected was detected in the 5 second integrations. In fact, we first localized it in the 5 second integration, kind of amazingly. So that was So on the sort of second or longer time scales, it's much easier to go after with interferometers, I think. So maybe it's you know, the parameter space is between 10 milliseconds or something like that, and about a second. And after that, with an interferometer, you can nab the sort of 1 second long things, except for the DM. If the DM's longer than the integration time, we're not really thinking about that. So maybe we have to go back there again. But maybe at that sort of time scale, interferometry is kind of not so bad.
You don't mean that the FRB was 5 seconds long, right?
No, the FRB, including DM dispersion, was, I don't know, half a second or something, and it happened to sit inside a 5 second integration window in the interferometry. And so when you made an image of that 5 seconds, the FRB popped out.
Oh, okay.
Yeah. So that's work that Shivani Bandari did. I think she published it. I can't remember if it was this year or last year, but anyway. But it was also detected in the incoherent sum.
Caitlin Shin pointed out in the chat that there's not evidence for an unobserved population of intrinsically wide bursts.
Ah, okay.
The scattered ones seem to get missed, but is that right?
The super scattered bursts. What we're interested in.
It is interesting.
Oh, it was 10. Sorry, Shivani points out it was 10 seconds, not 5, and it was FRB 191001. Sorry, you were saying, Liam? Did I interrupt you?
Oh no, Emily just suggested that I share some of these figures from the chime paper where they show the selection function. So this one is in scattering time scale.
Mm-hmm.
And then this one, I guess, is pulse width more generally. I'm amazed at like how flat and how complete the chime FRB search is. This is kind of the one parameter where you really do miss large numbers of events. And it makes sense because an FRB that's scattered at 3 milliseconds at L band is 100 milliseconds for chime. So we already know that there's plenty of those.
Adam has his hand up. Adam, do you want to chime in? Sorry,
Yeah, I just wanted to say that I think that the crossover point towards doing searches for wide bursts using imaging searches is quite a bit shorter than, you know, the kind of 1 second time scale. Because I think what you're referring to, Keith, is doing no de-dispersion and just looking for image domain transients using fast imaging and just, you know, frequency averaging over the whole band. But of course, yeah, you've got approaches like real fast and like Krakow with Craft that go down to, well, aim to go down to like kind of 1 millisecond, well, a few millisecond timescales doing image-based searches with de-dispersion. And so I think, you know, the beamform searches are effective up to maybe like 10 milliseconds, 20 milliseconds, and then they start to drop off because of the gain variations that are coming from, you know, that are intrinsic to beamform data, because you've got the autocorrelations being included as well. But it's actually, I mean, we want to push down to like kind of 1 millisecond with these imaging searches, but so we can very easily do, well, relatively very easily do, you know, 10, 20, 30 millisecond integrations with those imaging searches and not be constrained by the kinds of problems that you have with beamform searches, because you're just using imaging that doesn't have the autocorrelations in it. So I actually think that the technical crossover point is actually fairly nice for us. Like it works fairly well.
Yeah, I forgot the thing I'm doing at the moment that consumes my entire life is exactly what you're saying. But currently I wasn't planning on getting out to, you know, hundreds of milliseconds of width, but maybe it's worth a go. I mean, I don't know whether, I mean, just getting back to Kendrick's point about what are the interesting FRBs, you know, high redshift is one, but is very highly scattered another thing that's interesting, or are they kind of boring anyway? You know, I mean, and along the same lines, I remember thinking like, if I could point an ASCAP field of view anywhere and try and get something useful out of a handful of FRBs, what's an interesting direction? And we were thinking, oh, you could look around, some clusters or the LMC or the SMC to measure, what's the actual DM contribution of the galaxy halos, as an example. But in that case, do you really need to have high sensitivity to large, very wide pulses so that you can recover these things? And or is, I don't know. I think the the width thing, well, the highly scattered thing, arguably, I don't know whether it's as interesting or not.
Well, I would say regardless of whether or not it's interesting, it's cheap. If you're going to search down to a timescale of X, searching on timescales of X times 2 to the power a lot is relatively cheap.
Yeah, sure. Yep.
I think a lot of what you'll see will just be composite pulse trains and stuff like that. You'll see what Daniele saw, which looks like a 3-second burst if you zoom out, or what we've seen from R3, where you have 15 micropulses in a row spread out over 40 milliseconds, for example.
Yeah, and if you catch those and you save your baseband data so you can go back and like zoom in on them, then I think that's potentially quite valuable.
Yeah, definitely.
Oh, there's lots of stuff coming up in the chat. I don't know whether I haven't actually managed to follow it yet. If someone wants to put their hand up and summarize. Oh, there you go. Still Finney says Virgo cluster is interesting for sources than cluster DM or coma if you've got a smaller beam. Thanks, Still. I'm just trying to go through some of these things. If you do an Ron says, if you do an interferometer imaging search for long bursts, can you modify the spectral line mode to a DM search mode? I'll have to think about that one, Ron. Zoroar, maximize star formation rate in the field of view for a given survey depth. Oh, yeah. Actually, Shivani had a thought about this. We went out and, if I remember rightly, Shivani, she kind of went to try and do exactly that, given a field of view, go out and find as much star formation as you can on the sky. And I think we ended up finding a couple of favorable directions, but they weren't favorable by a factor of 10. I don't know, maybe Shivani, if you can remember what that results of that investigation were, you can pop your hand up. Yeah, I mean, I actually have missed a couple of the sessions, I'm afraid, so I don't know where we're up to on star formation, on proportionality with star formation rate and FRB rate. Or for favorable directions on the sky on different scales. No one's going to bite on that one. Oh, I've exceeded my time, I'm afraid. Am I handing over to you, Liam?
Is it on me? Okay.
Hang on, let me do. Can I do? Do I have to do anything?
No, I don't think so.
Okay.
I've sort of exhausted my hobby horses, so maybe I'll just give it an open floor. Is there anything people want to hear the broader community discuss in our last 20 minutes? Okay, well, if not, I can talk more about the cluster stuff and more specifically the intergroup medium. So Vikram and I just put out this paper this morning. It should be arriving, I think now, basically on the archive, where we claim to have detected the CGM and the intergroup medium using chime FRBs for nearby galaxies. And as I mentioned during the slides, the highest DM source in the whole chime FRB catalog 1 seems to be within about a megaparsec of a galaxy cluster. So this isn't about maximizing detection rate by looking at large scale structure, by looking at star formation. This is about intersecting halos full of gas. So have other people been thinking about this recently, especially with 500 chime FRBs now public? Actually, Kendrick, since you were closely involved in the work, the cross correlation result with CHIME and optical galaxies. What was the stuff about the local dispersion? Something like 400 units of DM.
Oh yeah, so my student Masood Rafi Ravandi is giving a talk on this next week on Tuesday, I think. So I don't want to steal his thunder too much, but you know, one thing that we found when we did statistical cross correlation between FRBs and galaxies is that you know, there's a statistical association between galaxies at redshifts of around 0.4 and FRBs with DMs of around 800, which would suggest you know, host DMs around 400, which is sort of surprising. It's a rare population, so it would be it would mean that you know, there's a small population of FRBs that are associated with like galaxy clusters at redshift 0.4. We did we thought about a lot of a few different possible explanations for this result, and the two ideas we came up with were either FRBs that are close to the centers of very large halos. That would be a rare population that would, you know, there's a small probability of an FRB at redshift 0.4 being near the center of a large dark matter halo. But it would explain the observations. And you know, another possibility, which I guess is less likely, but I'm not actually sure about this, is that it could be lensing induced, strong lensing induced. If large clusters are magnifying background FRBs.
Interesting.
But you're saying, it sounds like you, we had the statistical version of the statement and you had the single object, you have the single object version of the statement where there's one FRB at very high DM.
Oh yeah. I mean, that was just kind of curious. I looked at a cluster catalog and did some cross matching. The problem is with the cluster catalog, because the volumetric rate of clusters is so low, you don't know that they're in the foreground. And so you don't know that the FRB has actually intersected it. It was just interesting that literally the highest DM source is within a virial radius of a cluster.
Oh yeah.
The work we did was all with galaxies within about 30 megaparsecs or 50 megaparsecs, so that you know they're in the foreground.
Okay. Yeah, large galaxy clusters can have DMs of order 1,000 if the line of sight is close enough to the center.
Yeah. Matthew, do we have any stats on how broadband? Oh yeah, maybe we could switch to Starlink. Seems appropriate. Matthew, do you want to come on mic again? Or Zoroar? To talk. There we go.
Hello.
Hey.
Yeah, I think Starlink's up at 5 or 6 gigahertz, so it doesn't affect FRBs too much. I don't know when the next generation of LEOs is going to come along and hog our bands, but I think there's easier bandwidth for them up at higher frequencies that they'll take first.
When can we expect 100,000 LEO satellites?
I don't know that. I think it's probably a bigger issue for things like LSST than us.
Yeah, I think so too. Ron has his hand up. Sorry, I let this linger.
Yeah, I was just going to make 2 comments about the on the Starlink question. Luckily, as Matthew said, it's probably out of the band we'll be searching in. But just yesterday, we were discussing how we could do this search for FRBs at higher time resolution. And one suggestion from Ryan was we need to go to higher frequencies. And so that reminded me that the focal plane array technology, which we have developed, is being commercialized for all sky satellite communication system. So the idea is because of these new satellites, you need hundreds or even thousands of beams simultaneously. So I said, well, can we grab one of these and use it for FRB searching instead? So that might be an extremely indirect advantage we get from technology development because of this high density of satellites. My other comment is I'm moderately optimistic that we haven't really exploited RFI removal with much sophistication yet. That is to, adaptively cancel out RFI. It's all technically possible at radio wavelengths. And so the technology might keep our nose above water as the situation gets worse.
Nice.
It's technically possible while things are linear. It's not technically possible once they go non-linear.
Yep, I agree. So it's the stuff which can be out of band driving your system non-linear, and that will indeed be a problem.
The bandwidth of those all sky telecoms paths is pretty narrow because the downlinks are very narrow band. So you might need a special custom one on broadband, because 1 square meter of collecting area doesn't buy you a huge number of FRBs, but maybe you'd get the odd magnetar flare in the galaxy or something.
Yep. The current design only has 50 megahertz of bandwidth.
Okay, Sterl has a question for Kendrick, which is, could it be that the luminosity function is such that chime fixed limit is effectively distance limited, such that redshifts are always less than 0.4? So the high DM sources are almost always high host or intervening DM rather than cosmological.
Oh yeah, so I think it's important to say that the redshift distribution of FRBs is a flux dependent quantity. It could be at the chime flux limit. We can only see out to redshifts of order 0.4, and so we're finding that in our sample FRBs at DM 800 are associated with those redshifts. But if you could go fainter, you could look deeper and find FRBs at redshift 0.8 with lower host DMs. That's absolutely a possibility.
Yeah. But yeah, generically, if you have some relatively wide distribution of local DM, and you combine that with an Lmax or a cutoff somewhere, then you're going to end up with a DM distribution that kind of looks like what you guys have seen with chime, which is a pretty pronounced peak. And yeah, you might find that everything above 2000 is in a really dense environment or intersects a cluster.
Yeah, absolutely.
What is SATCOM?
It's an effort to put together a lot of people who are, both community, community members that are concerned with their own view of the night sky, but also people who are technically, like people in LSST and all these things. It's basically, measuring the impact, the anticipated impact by these satellites. So they're doing spectrum studies and things like that. I haven't been involved as I wanted to, but they're also making, it's sort of an effort to get into the government and actually put in policies that protect the night sky or the day sky for radio astronomers. But I think radio astronomers have been less involved than optical astronomers in this effort. But I think it's quite important. I think a lot more people should be involved in it, and that's my ploy of this type of satellite. And obviously the radio spectrum is managed quite closely in different countries, but this is international, not quite waters, international ether. So it's something interesting that is coming into worldwide attention.
Yeah. Okay, Ron's hand up is up.
I was time sharing between FRBs and a meeting we had yesterday on what radio astronomy you can do from the moon. And a particular discussion that's relevant for this is the value of getting to the lunar far side as the ultimate radio protected site. But Tasso Sumas, who's involved in spectral regulations, made some pretty scary comments. First of all, that these commercial multiple satellite systems ignore regulations, have not been subject to a lot of the regulations that have been painstakingly worked out for the Earth. And he said the situation with the moon is disastrous. As soon as they decide to put a cluster of satellites around the moon, the only real radio quiet site in the universe disappears. And the concern is that internationally, there's not nearly enough being done to try and get this back under control.
Okay, thanks. Yeah, I mean, again, if anybody has any questions or comments, please go ahead, but I don't think it would be the biggest deal in the world if we ended 8 minutes early. What do people think? Okay, great. Well, thanks for attending, everybody. And see you all tomorrow.